Okay, good day. So let's have another example for the double integration method. Okay, for example, we have this beam loaded as shown, and we are required to determine letter A, that is EIY at midway between supports. That is, EIY is the same as the deflection equation. Then we have letter B, that is EIY at point E. So to establish our deflection equation, we need first the moment equation, and before that, we need to compute first for the support reactions. So let's say we have the reaction at A. So this is, let's say, RA, and at the roller support, this is, we have R sub D. So here we may do the summation of moments at A equal to 0, clockwise moments to B, assuming clockwise moments to be positive. So we have that 400 newtons with a length of 3 meters. Its point of action will be at a distance of 1 plus half of its span, 3/2, plus the 600 newtons at the free end, that is at a distance of 8 meters, minus the reaction at D. This is at a distance of that is at a distance of 6 meters equal to 0. So computing for the reaction at D, we have that as 400. This is multiplied by 3, multiplied by 1 plus, this is 3/2, plus the 600 newtons multiplied by 8 meters. This is to be divided by 6. We have R sub D is equal to 1,300 newtons, and it is upwards. Then we to compute for the reaction at A, we do summation of forces vertical equal to 0, assuming upward forces to be positive. So we have that as R sub A plus R sub D is 1,300 minus the 400 multiplied by 3 minus 600 equal to 0. So we'll be having 1,300 minus 400 by 3, then minus 600. So we have that as 500. Transpose, it will be positive, which means correct assumption. 500 newtons, that is upwards. So after computing for the support reactions, so we have RA is equal to 500 newtons, and RD is equal to 1,300 newtons. So after computing this support reactions, so we are now to establish our cutting section at a distance x from the left of the beam. So we may assume a distance, let's say, to include all forces. We are to assume a distance x just before the free end. Let's say this is at a distance of x. Then so we have the support reactions. This is, we have the support reaction at A. This is 500 newtons. The support reaction at D, that is equal to 1,300 newtons. As you can see on this figure, so we need to extend the 400 newtons, the 400 newtons per meter up to the right end, or up to the cutting point or cutting section at a distance x from A. To avoid problems, how do we express this 400 newtons in terms of the moment equation, in terms of x? So in Tagalog, bakit natin kailangan i-extend yung 400 newtons to the right? Para maiwasan natin yung problema, how do we express this 400 newton meter doon sa moment equation natin in terms of x? So we are to extend this 400 newton meter from point C up to our cutting section. But to nullify the effect of this 400 newton meter, we are placing a 400 newton per meter upwards, just to cancel out. So again, the purpose is just to simplify how do we express this 400 newton meter in our moment equation in terms of x. Alright, so let's have our moment equation. Okay, for the moment equation, I'll be starting with the reaction at A, that is 500 Newton meter. So this is our moment. We have the magnitude of the moment is equal to 500. So 500 newtons is at a distance of x. Then what about this 1,300? This 1,300 is at a distance from our cut section. That is at a distance of, if this is 1 plus 3 plus 2, that is 6 meters. And this is x, that is at a distance of x minus 6. So that is plus 1,300, its lever arm is x minus 6. Then we have this, the 400 newtons per meter, the upward 400 newton per meter. What is this distance? From A to point C, this is 1 plus 3, that is, we have 4 meters. So therefore, we'll be having the span of the 400 newton meter that is upward. Its span will be, obviously, this is at a distance of, or the span is equal to, this is x minus 4. So that is plus, we have 400 newtons per meter. Its equivalent resultant will be x minus 4. What about its lever arm? Its lever arm is in between the distance x minus 4. So this is x minus 4 divided by 2. Then we have the 400 Newton meter downward. So we are just to analyze this as a single uniformly distributed load, from point B up to the cutting, up to the cut section. So what is this distance? So this distance, all we have to do is subtract 1 meter from x. So this is at a distance of x minus 1. Its equivalent resultant is 400 multiplied by its span, that is the x minus 1. What about its distance from the cut section? That is at a distance of x minus 1 divided by 2. So this is minus, so that is minus, we have 400, its equivalent resultant is x, 400 times x minus 1. Then its lever arm, with respect to our cut section, that is at a distance of x minus 1 divided by 2. So simplifying our moment equation, that is the 500 multiplied by x plus 1,300 multiplied by x minus 6 plus, this is 400 over 2, that is 200. This is multiplied by x minus 4 squared minus the 400, that is also 400 over 2. So this is 200 multiplied by x minus 1 squared. So this is our moment equation. So for double integration method, for the double integration method, what is the equivalent of our moment equation? That is the same as the EI y double prime, or the moment equation. This is now equal to 500 of x plus the 1,300 multiplied by x minus 6 plus 200. This is multiplied by x minus 4 squared minus 200. This is x minus 1. X minus 1 squared. This is our moment equation, or the EIY double prime. So we are now ready to perform the first integration. So we are integrating both sides of the equation. So what is the integral of EI is constant. What is the integral of y double prime? That will be EI y prime. So this is the same as we have 500 x squared divided by 2 plus 1,300. This is multiplied by x minus 6 squared divided by 2 plus This is 200 multiplied by x minus 4. This is raised to 3 divided by 3. Then minus, this is 200 multiplied by x minus 1 cube. This is divided by 3 plus the first arbitrary constant. So we are simplifying this. This is the slope equation. EIY prime is now equal to 250x squared y plus, what is 1,300 divided by 2, that is 650. This is multiplied by x minus 6 squared y plus the 200, this is divided by 3, y multiplied by x minus 4 cube minus the 200, this is divided by 3 multiplied by x minus 1 cube plus the arbitrary constant, or the first arbitrary constant, c sub 1. Take note that this is the slope equation. So from the slope equation, if we are again to integrate both sides of the equation, we will be having the deflection equation. So this is the same as we have the EIY is now equal to 250 x cubed divided by 3 plus 650, this is multiplied by x minus 6 cubed divided by 3 plus we have 200 over 3 multiplied by x minus 4, this is now raised to 4 divided by 4. Then minus the 200 divided by 3 multiplied by x minus 1 raised to 4 divided by 4 plus c1x plus the second arbitrary constant. So this is our deflection equation. Then we may first simplify. This is, we have EIY is equal to, this is 250 divided by 3 x cubed plus 650 over 3. This is multiplied by x minus 6 cubed. Okay, plus, what is 200 over 4? 200 over 4 is 50. 50 over 3, okay, multiplied by x minus 4 raised to 4 minus, so 200 over 4 is the same as 50 over 3, multiplied by x minus 1 raised to 4 plus c1x plus c sub 2. So this is our deflection equation. So one disadvantage of the double integration method, it is a very long procedure or a very long method. Okay, so to complete our equation, we need to compute for the values of the arbitrary constants, that is the C1 and C2. So all we have to do is focus on the supports, wherein obviously at supports we don't have a deflection. So that is at A and at D. Okay, so let's say that is at x is equal to 0, that is at A. That is at A, that is we have the hinge support at the left end. Take note that if we are if we are using the double integration method, our horizontal axis is the x-axis and vertical is the y-axis. So to imagine the deflected form of the beam, we are to draw the elastic curve. So this is the, let's say, the exaggerated deflected form of the beam, also known as the elastic curve. Okay, so let's have at x is equal to 0, that is at point A. Take note that at point A is a support. So at support, take note that we don't have a deflection. That is y is equal to 0. So if we are to substitute from our deflection equation, that is, we have now EIY at A, that is y is equal to 0, 0 deflection. This is 250 over 3 times 0 raised to 3 plus 650 over 3. This is 0 minus 6 cubed plus 50 over 3 multiplied by x minus 4. This is raised to 4. Then minus 50 over 3. This is multiplied by 0 minus 1 to the fourth. Then plus, this is plus c sub 1 times 0 plus the c sub 2. So we have the 0 terms. This is now 0, 0. What about if we are to encounter this one? We have the 0 minus 6. Also this one. It should be the 0 minus 4 and 0 minus 1. Take note that if you are doing the double or using the double integration method, for example, we arrive at a value, let's say x minus a, and the result is a negative value. Okay, we assume this to be, or we simply have that value. If it is a negative, let's have x minus a will be simply equal to 0. Why? Which means since we are using a bracket method, which means if we arrive with a negative value, that point is not on that bracket, or we are not yet at that section. So we neglect. Basically, if we arrive with an x minus a, and we arrive with a negative value, we simply neglect, or simply assume it to be also equal to 0. So therefore, basically, we have c sub 2 is equal to 0. In most cases, if we have a simply supported beam, the value of c sub 2 is always equal to 0. Okay? For the case of simply supported beams. Then, how do we compute for c sub 1? We proceed to the next support. That is at x is equal to 6 meters. Take note that is at point D, at the roller support. That is at a distance of 6 meters from A. Again, that is at point D. So what we have to do now is substitute. Okay, from our deflection equation, so we have that is EI y is 0 is equal to, this is 250 over 3 multiplied by 6 cube plus 650, this is divided by 3, this is multiplied by 6 minus 6 cube, plus the 50 over 3, this is multiplied by 6 minus 4, this is raised to 4, minus, we have the 50 divided by 3, multiplied by 6 minus 1, this is raised to 4, plus c sub 1 times 6, plus c sub 2 is 0. So we have this term as 0, the 6 minus 6. The same with the EIY, since y is equal to 0. Again, at x is equal to 6 meters, that is support D, the value of y or the deflection is equal to 0. So computing for the value of c sub 1, we have that as 250 over 3, this is multiplied by 6, plus the 50 over 3, this is multiplied by 6 minus 4 raised to 4. Then minus the 50 over 3. This is multiplied by 6 minus 1. And this is raised to 4. And to be divided by 6. So we double check. That is 250 over 3. And this is multiplied by 6 raised to 3. Okay, plus the 50 over 3. This is multiplied by 6 minus 4 raised to 4. then minus the 50 over 3, then multiplied by 6 minus 1 raised to, this is raised to 4. That's 7,850 to be divided by 6, then transpose. It will give us a negative value. It should be negative 3,925 divided by 3. That is 3,925 over 3. And negative since we are to transpose that value. So we have now the value of C1. So now we have the complete equivalent of the deflection equation. That is EIY is equal to 250 over 3 of x cube plus 650 over 3. This is multiplied by x minus 6 cube. Then plus, we have the 50 over 3. This is multiplied by x minus 4 raised to 4. Then minus the 50 over 3 multiplied by x minus 1 raised to 4. Okay, plus that is minus, since C1 is negative, minus 3,925 over 3 of x. So this is the complete deflection equation. EIY is equal to 250 over 3 x cubed plus 650 over 3 multiplied by the quantity x minus 6 raised to 3, then plus 50 multiplied by the quantity x minus 4 raised to 4 minus 50 over 3, the quantity x minus 1 raised to 4 minus 3,925 over 3x. Okay, let us now compute for the required. Okay, so after having the equation of the deflection equation, we can now determine the deflection at any point of the beam. So we are to determine the required. Letter A, so EIY or the deflection equation at midway between supports. So between supports, we have the supports A and D. They are 6 meters apart. So in between, that is at x is equal to 3 meters. So basically at A, we are looking for the equivalent of EIY at a distance of 3 meters. So we have letter A, the equivalent of EIY at x is equal to 3 meters. So we substitute the value of x in our deflection equation. This is EIY equal to the 250 divided by 3 multiplied by 3 cubed plus 650. This is divided by 3 multiplied by 3 minus 6 cubed. Then plus we have 50 over 3. This is multiplied by x, or that is 3 minus 4 raised to 4 minus the 50 over 3 multiplied by 3 minus 1 to the 4th. Then minus 3,925. This is divided by 3, multiplied by the value of x, that is 3. So we may simplify some of these terms. This is 3 cubed. Let's say this is now 3 squared. If we are to cancel the denominator, again we have this term. 3 minus 6 is negative 3. If we have that negative, we neglect this term. So as good as 0. The same with this one. 3 minus 4 is negative 1. That is the same as 0. Then we may cancel this. The 3, 3. So we have the equivalent. The equivalent of EIY at x is equal to 3. So that is the same as 250. We cancel the denominator. This is multiplied by 3 squared. Then minus the 50 over 3. This is multiplied by 3 minus 1. That is positive. So we are to consider this term. 3 minus 1 is positive 2 raised to 4. And then minus 3,925. We have a wrong grouping in our calculator. That is 3 minus. Okay. That is negative 5,825 over 3. So it's negative 5,825 over 3. The unit for EIY or the deflection is the Newton meter cube. Then if you are to observe, the sign is negative, which means the deflection is downward. So this will be our answer for letter A. Then for letter B, so EIY at point E. So at point E, that is at a distance of x, that is at the free end of the beam. So we are to consider the value of x equal to 8 meters. So basically for letter B, we are looking for the equivalent of the deflection at x is equal to 8 meters. So this is for letter B. We have EIY at x is equal to 8 meters. So we are to substitute the value of x in our deflection equation. So we have that as, we have EIY is equal to, this is 250, this is divided by 3 multiplied by 8 raised to 3 plus 650, this is divided by 3 multiplied by 8 minus 6 raised to 3 plus we have 50 over 3. We have 8 minus 4, this is raised to 4 minus the 50 over 3 multiplied by 8 minus 1. This is raised to 4 minus 3,925. This is over 3 multiplied by 8. Alright, so computing for the value of EIY. So this is 250, this is divided by 3, multiplied by, this is 8 raised to 3. Okay, then plus 650, this is divided by 3, then multiplied by 8 minus 6, this is raised to 3. And then plus, we have the 50 over 3 to be multiplied by 8 minus, this is 8 minus 4, then raised to 4, then minus, we have the 50 over 3 multiplied by, we have 8 minus 1, this is raised to 4, and then minus 3,925, this is over 3 multiplied by 8. So we have that as negative 5,450 over 3. Negative 5,450 over 3 Newton meter cube. So again, we have this negative sign, which means the deflection is downward. So this is our answer for letter B. This will be our solution based on the requirements for this example.